Math 242, Cuesta College. I'm Joe Vasta. It's pre-calculus, and we are covering 6.5 today. 6.5, the title is called Applications of Exponential and Logarithmic Functions. We're going to mostly, or maybe 100%, do the applications of exponential functions. There's a lot in 6.5, and we're going to cover some of it. And the first thing that we're going to cover happens to be compound interest and continuously compounded interest. So, wow. And we have these formulas you may have seen in another class. And what we're going to do at the beginning is derive these formulas. And after we derive the formulas, we'll start doing some problems. So for some of you who don't care about derivations, because you really don't have to do that in your homework, you can just skip the video ahead, slide it ahead until you see problem number 1. So here goes the derivation of these formulas, this one being first. And what is this P and this R and this N and this T and this E? Let's take a look at this. Okay, so hopefully we can see this clear enough. If it is a little blurry, you do have this on my website under the PDF right next to the video. So suppose you have an amount of money, A, and that's the amount that you're going to put into the bank. And, no, wait, let me start again. The amount of money is how much you have in the bank, okay? That's going to be A, and that's going to change because sometimes the interest off the money creates more money in your bank account. P is the principal, and that's the money that you're going to start off with. And for this problem, it will be $100. R is the annual rate, which is 12%. We'll just assign it to that, or 0.12. And N is the number of times the money is compounded per year. So let's go ahead and say if N equals 1. Now this would normally be a PowerPoint, but we're just going to do this here. If N equals 1, if it's compounded 1 time a year, how much money would you have? Well, just ignore this part now. You would have your money 100 plus a little more. It would be 100 times 0.12, and we had to use the decimal there. So that's like, what is that, $12? And so you'd have $112, which we have written there. But what I'm going to do, and not that we needed to do this to get the 112, so I'm going to factor a 100 out to the front, and I have 1 plus 0.12, which is 1.12, and that's just another way of looking at that. That's going to actually help us with something down the line. So now, what we're going to do is we're going to let N equal to, this is really high tech with the pieces of paper covering up things. Oh well. So how much money would you have if instead of being compounded once a year, it was compounded twice a year? So compound it maybe at the end of June and then at the end of December. Okay, now when it gets compounded twice a year, they do not compound it 12% at the end of June and 12% at the end of December. They would actually compound it at 6%, 6%. So they cut that in half each time they compound it. So let's go ahead and see what this gives us. A1 is the amount of money you'll have after they compound it the first time, which would be 100 plus 100 times 0.06. So this is at the end of June. And so when you do that, you end up getting that right there. You end up getting $106. Now this is not, we're not done. This is not our final answer. It's going to compound at the end of December. So at the end of December, we have A2. And this is the cool thing about compound interest. It's now going to compound your $106 that we computed right here. It's not just going to do it on the 100. So you have 106 plus 106, and here's the end of December, times 6%. And so when you have that, you end up having 106 times 1.06, which gives you $112.36. So when you compound it twice, you make a little more money than when it's compounded once. Now, I know some of you are like 36 cents, that's not much. But if you had more money, then it would be a little bit more money. So that is how you do that, but notice what happened with my 100. With my 100, to get this, I multiplied 100 times 1.06, and then I multiplied it again by 1.06. So I went like 100 times 1.06 times 1.06, and I ended up getting 112.36. So what does that mean? It means that I could get the amount by going 100 times 1.06 squared to get this. So now I'm going to go ahead and change the n to equal 4. And when n is 4, look what I have here. I just go 100. And instead of going 6%, because I'm compounding it 4 times or quarterly, 4 times a year, I'm going to chop this into 4. I'm going to divide it by 4, and that's going to be 3% each time. So instead of going 1.06, because that was 6%, this is 1.03 raised to the 4th, and it gives me $112.55 cents, which is more than the last one. Now, if you follow the formula, if you're going to compound it n times per year, let's just see if we can get this. The 100's on the outside. I have 1 plus, kind of like what I had here, and then I take my rate and divide it by whatever number that was. So that's why this says 1 plus r over n, and then this number right here, as you can see, is how many times it gets compounded a year. So that's where we didn't derive the formula completely, but we're getting there. So now let's take a look at this. It says if n is 4, which was like in the last example, and we're going to do this for 3 years, then we're going to have not 4 for the exponent there, but it's actually going to be 4 times 3. It's going to have, you're going to be compounding it 12 times in the 3 years. And so this gives me $142.58, which is a lot more than the $100 I started off with. So our formula, if we throw t, which is the number of years in there, is to actually put a t up next to that n, just kind of like what we had there. And so there is the compound interest formula that we had written on the first page. It looks like this, and then we have an extra t up there. Okay, so that gives us compound interest. You don't have to know this derivation, but this is just for the 1.5 students. I don't know where I'm getting the 1/2 from, but 1.5 students who really care where things come from. Now, here's something, a result from analysis or calculus, is if you've got 1 plus r over n raised to the n, which we kind of have within there, if you make n get really, really big, like you put 1,000,000 in for n, and then put 1,000,000,000,000 in for n, and then 1,000,000,000,000, and then those are some numbers that, like, the Congress of our country, I mean, that's how much money they spend per year or whatever, so they have no big issue with that. But if you put really big numbers in for n and you just make those numbers bigger and bigger and bigger, this expression right here goes to e, which is that 2.7 constant that we did earlier, raised to the r. See, it says as n goes to infinity. And when you hit calculus, you're going to be doing something called limits, and that's kind of what we're looking at here. So if that part, so this part right here, let me circle it in orange. That part right there, if n gets really, really big, that orange part, not including the t, goes to e to the r. So you have e to the r raised to the t. You end up getting something called continuously compounded interest, which now this formula becomes e to the r, so you see e to the r there, and then a power to a power, you multiply the exponents. And so that is continuously compounded interest, and that's if the number of times you compound per year is infinity, which infinity is not a number, but we'll talk about why this is useful in the banking world. Now, some of you might go, well, I don't put money in the bank and save it. These formulas apply when you have a credit card and you owe money on the credit card and you're not not paying it off every month and you're making the minimum payment. This is how they will charge the interest. They will use these formulas and it compounds. So let's take a look at what we've just derived. We derived those. There's the compound interest formula and the continuously compounded interest formula. I think right now is the time where we start doing problems that are found in your book or ones that are like these ones. Okay, so we'll just hope that it is clear enough. $1,000 is invested in an account which offers 3% compounded monthly. So let's see if we can do problems like this. Okay, so $1,000 is invested in an account. Okay, the first thing we want to realize is that 1,000 is going to be the principal. It's invested in an account which offers 3% interest. Now 3% written as a decimal is 0.03. And it's compounded monthly. Compounded monthly means how many times a year? It means it's compounded 12 times per year. So this is what we're looking at for our problem. Now part A, and I'm going to actually do these parts below here, and even if it means I have to go to a blank piece of paper, I don't mind. Find the amount in the account in terms of T years. So let's write up that formula. I'm being a little redundant here. Writing up the formula that I had derived and that I had written on the first page. And basically, we know P and R and N. So let's go ahead and plug those into the formula. So we have 1,000. We have 1 plus R, which is 0.03. You definitely want to put that as a decimal and not as keep it as a percent. You don't want to do that. Keeping it as a percent, we have 12, and then this is N, which is 12, and then T. So on this, we can actually crank this in our calculator here. And so what I'm getting for this part is 1,000, 1.0025 raised to the 12t power. This gives us the amount. And so find the amount A in the account in terms of T years. There it is. Now, if you want, this is a stylistic thing, you can call that A of T. Okay? Let's go ahead and do part B. And maybe you may be able to do these on your own, pausing the video and seeing if you can figure them out. But if not, let's go ahead and do this. Determine how much is in the account after 3 years. So this is a function, A of T. I'm going to go A of 3. And when I go A of 3, I'm plugging 3 into this function. This is 1,000 times 1.0025, 12 times 3. So in your calculator, you're going to go 1,000 times 1.0025 raised to the 36th power. I'm going to go ahead and do that right now on the calculator. And then we raise it to the 36th power. I'm getting a lot of money. So I'm rounding it to the nearest penny. So I'll just say this equals, this is how much money you'll have. $1,094 So that's how much money you have. After 3 years at 3%, your $1,000 just made you $94.05 richer. Now, of course, today, the interest rates might not be 3%. In fact, as I'm speaking, they're a lot lower. But in terms of credit cards, sometimes those interest rates are a lot higher. So just doesn't seem fair, but it is what it is. Let's go ahead and, like how some credit cards could have 20% interest rate. But you know, I mean, you agree to that when you're borrowing the money, I guess. Oh, okay. So actually, we better leave this like this, because part C says, determine how much is in the account after 30 years. So after 30 years, you're going to go ahead and put 30 into the function. Time is measured in years in these problems. So you're going to actually go 1,000. So we're looking up here. 1.0025. And then we go 12 times 30. Now I've already done this calculation, and I ended up getting on my calculator after 30 years $2,456.84. So your money more than doubled when it hit 30 years. So your original investment, and you can't see it because it's way up there, but it was $1,000. Okay, now the next problem says, determine how long it will take for the initial investment to double, round to the nearest tenth. Okay, in terms of the years. So how long will it take to double? Well, this is an interesting question because we have our function here. It has the input is time, and the output is the amount of money in the account. And in part D, hopefully we still see D, good. It's asking us in part D, how long will it take the investment to double? So they're asking you this right there. They're saying how long? Which means you're trying to find out what time it is. And it says the initial investment. The initial investment was actually $1,000. That was the principal. So when it doubles, it's not going to be 1,000. It's going to be, the amount will be $2,000. So look what we have here. We're still going to stick something into this function, but we're not going to put the input in of t. We're actually going to put the output of 2,000 in there and solve for t. So let's go ahead and do that. So see this equation that has a box around it? I'm going to go ahead and use that. So A gets replaced with 2,000. And then we have 1.0025 12t. And look what we have here. So we were holding off on the applications, but now here is a great application of an exponential equation. And so when we were solving them, maybe they were kind of boring, but now we can make a connection with money or biology or engineering or something that we care about. Then you start saying, well, maybe these aren't such bad things. I'm going to turn this into a basic exponential equation by dividing both sides by 1,000. So I end up getting 2 equals 1.0025 raised to the 12t power. This is a type 2 exponential equation. I can't not get a common base, so I'm going to ln both sides. the reason I ln both sides is so this guy right here can jump out front using the power rule of logarithms. So I have ln 2 equals 12t ln 1.0025. Now I'm trying to solve for t. I'm almost there. I just have to divide both sides of this equation. The yellow highlighter smeared a little by 12, in which those 12s will cancel. And I'm also going to divide it by ln, which is just some crazy number, 1.0025. So this is ln 1.0025. You're definitely going to need your calculator for section 6.5. And so those cancel out as well. So let me rewrite it, and I'm going to put the t on the left-hand side. T equals ln 2 all over 12 ln 1.0025. Now when you enter this into your calculator, make sure if you're doing it all in one thing to put parentheses around there, or it's just going to divide by 12 and then multiply the result by ln of that other stuff. I'm going to go ahead and do this on the calculator, put in my parentheses, and 1.0025, and I end up getting 23, so this thing, when I do this on the calculator, is 23.133775, okay, and it just keeps going. And so they ask us on the problem, round to the nearest tenth. There's the tenth. So how long does it take the money to double? 23.1. It's a time, and the time is measured in years. And so that completes problem 1, which had 4 parts to it. And we've actually seen how logarithms can help us do something in the real world. Let's go ahead and do problem number 2. $1,000 is invested in an account which offers 3%, and then look at the compound it continuously. So this is kind of like the last problem where we have the principal is $1,000, the rate is 3%, so I'm going to go 0.03, and n, well, there is no n now. This is continuously compounded interest, so this is what we have here. Part A asks us to find the amount in the account in terms of t years. So what we're using for this, since it's compounded continuously, we're using this formula. So don't bother to memorize these formulas. I'm going to actually put them on the test if you need them. So I'm going to write this. Sometimes people call this the Pert Formula. Let's go ahead and write it out. The amount equals P e to the RT power. And so the principal is 1,000, E, and then R is 0.03, and then here's T. So maybe writing it a little nicer, I can say the amount equals, well, there's not much more I can do with the right-hand side, 1,000 E to the 0.03 T. And I can write that as A of T if I'd like. You know, so I'll kind of point that out there. Okay, now you might wonder, well, what is this compounded continuously? Why would anybody even care about this when banks are not compounding things continuously? Because this is still a calculation that finance people will do to give us upper and lower limits on things. which is actually something kind of remarkable. And the formula does look simpler than the other formula that we had on 1A. So let's go ahead and we're going to actually compare some of the answers that we get from the other one, okay? Part B says determine how long, or determine how much is in the account after 3 years. We are going to write a 3. And we're going to put that into this function. So this is 1,000 e to the 0.03 times 3. So I'll go ahead and do that on the calculator, and maybe if you have your calculator, you should try to see if you can get the same answer. And actually kind of messed up here. Putting in, I forgot to put the point. Okay, so there it is. So what I'm getting for this is I'm getting $1,094.17. Now, if you compare that to what I got on problem 1B, it was $1,094.05. So this is kind of like an upper bound. Lots of mathy people and even finance people like to know what the upper bound is. And it's really not off by much. You'd think being compounded continuously would make you a lot more money than monthly. Okay, this one was compounded monthly. And we only made us, the difference is like 12 cents after 3 years. Let's go ahead and do part C, which asks, determine how much is in the account after 30 years. So I'm going to go A of 30. This is going to be 1,000 E, and we have 0.03 times 30. I'll go ahead and throw that in my calculator really quickly. So what I end up getting for the amount after 30 years with continuously compounded interest is $2,459.60. Now compare that with the answer that we got from compounding it 12 times a year. We're only off, so after 30 years, we're only off by a little less than $3. I mean, you'd think this would make a lot more. I mean, you think this one here, sorry, the one that we just did would make a lot more than this one, and it's not that much for waiting a whole 30 years. So that's why we have this formula. It makes a really good upper bound for a lot of the problems. Let's go ahead and answer the next question. It says, determine how long it will take for the initial investment to double, round to the nearest tenth. So that's what we're going to do now. And we'll try to keep the problem in there. And what is this? This is a blank piece of paper. Let's go ahead and do this. This is part D. And so it's the same as before, where they're asking you how long will it take to double. We don't know what the time is. That's what we're looking for. And the amount, well, if the initial amount or the principal was 1,000, we're looking at the amounts being 2,000. And we are going to plug it in where? To this formula right here. Okay, so A is 2,000. We got 1,000 there. E raised to the 0.03t. I'm going to divide both sides by 1,000. I'm going to end up getting 2 on the left-hand side and e to the 0.03t on the right-hand side. I'll turn it around because I actually like having this variable on the left-hand side. I'm going to ln both sides, ln e raised to the 0.03t equals ln 2. On the left-hand side, this thing's going to go pop. Why? Because that's log base e of e to something is just the something. So this is 0.03t equals ln 2. I'm going to move this up a little more. I'm going to divide both sides by 0.03. 0.03, and I have t equaling ln 2 over 0.03. I'm going to plug that into the calculator, and we're rounding to the nearest tenth. So what it gives me 23.1049 yada yada yada. Here's the nearest tenth, and so it looks like it will take 23.1 years for the money to double. Now compare that with what we got on part B in the first one. When we round it, it was actually the same thing, but if you kind of look out, you can see that this one is a little bit less than when you're compounding 12 times a year, infinite times a year. So it takes a little less time, but in terms of the rounding, we got the same answer. Okay, so that was part D. Part E. So let's go ahead and bring this like this. I'll get another piece of paper here. And so part E says this. What principal, so now the principal was 1,000, but now they're going to change things around for part E. What principal should be invested so that the account balance is 2,000 in 10 years? So maybe you don't want to wait 23 years for your money to reach $2,000. So you better put more than $1,000 in. And so they're saying what principal? So let's write out this formula again. A equals P E R T. Okay, so we are actually looking for this. Now I know what you're thinking. You're thinking, well, didn't it say the principal was 1,000 at the beginning? Yes, but part E is going to change it. It says, okay, we want to find out what principal should be invested so the account balance is 2,000. So this 2,000 is actually that value of A. And we want to know, so P, E, the rate is still going to be 0.03. They didn't say that they were changing that. And then we have T, which in this case they told you 10. So I'm going to put a 10 right there. So this is 2,000 equals P, E, 10 times 0.03 is 0.3. Now before you say let's ln both sides, we're trying to solve for P, and it's just P times some dumb number there. So I'm just going to divide both sides by that dumb number, and I'm going to end up getting 2,000 over e to the 0.3 equals the principal that I should put in so I would have $2,000 in 10 years. And so on my calculator, I'm going E divided by, 2,000 divided by E raised to the 0.3 power. And so when I did that, I end up getting the principal that I should have is $1,481, and I'm rounding this 64 cents. So if you put that in the account instead of the initial $1,000, then in 10 years you will have built it up to $2,000. So that is the deal. We have finished the finance part of 6.5, and now we're going to go ahead and do some biology problems. So let's go ahead and do biology problems. Get rid of this. Move all this stuff out of the way. Okay. Assume the law of uninhibited growth applies to a wildcat population in a certain region. Okay, and they give us some information. So what is the law of uninhibited growth? Well, it's sometimes called exponential growth. And what it says is this. You've got, I'll just write the formula down. You've got n equals n naught. Now that is just one variable, n naught, or n sub 0. That's a subscript. E raised to the k times t power. Now here's the funny part now, which is I can't even find so much paper here. It's right over here. This guy right here. It's pretty much the same formula. This is going to be your initial population, which is pretty much your initial population with money. Here's E. K is the rate of growth, so was R. There's time, and then A, and well, N is how much of the population you have after so many years or whatever it is, and A is how much money you have. So Pert is really this guy. These guys are the same formula, just different letters. Okay. We could be, and a lot of people are doing this in the media, they are making connections with this and the coronavirus and the confirmed cases, and it does seem to be growing exponential, which means that, you know, this is an exponential graph that shoots up pretty high. It's the airplane taking off. But with the coronavirus and other things, it can't just keep getting more and more people because there is a carrying capacity. There's so many people in the world. So what the coronavirus will do is it will appear to be following something like this, but then it goes on something called the logistic growth model, which means then it kind of flattens out near the top. And so let's talk about wildcats, because we don't want to, you know, maybe you're watching these videos and trying to escape thinking about that. So now we come back to this. K is called the growth constant, and let's go ahead and do this problem. So we have wildcat population in a certain region. The current population is 85. So that's going to be our initial population. The N naught is 85. In 2 years, the population doubles. So look at this. N naught is 85, and that's when t is 0. And then it says in 2 years, the population doubles. So what is 2 times 85? 2 times 85 happens to be 170. So when they give us this information here, they're actually giving us, really I should be writing the points like this, t comma n. It's like x comma y, but t comma n, and the first one is 0 comma 85, and the second one is like having what? 2 comma 170. So this is just giving you, this information is just giving you 2 data points. But the first one here, you know, like if you put in 0 for t, you know, that makes that a 1 there, and then you'll end up getting 85 equals n naught. So lots of times when you get this one, you just know to put the 85 right there. Okay? So your constants are n naught, k, and e is a constant. Your variables are n and t. So we still have to find constant k, and that's what they're asking us to find. Find the growth constant k. And we're going to plug this, or this data point, into this. Okay? So n is 170, equals 85. E, so this is part A, by the way. I just smeared the E, great. Raised to the K, we don't know what that is. And then T is 2. So I have, I'll divide both sides by 85. And 170 divided by 85, that happens to give me 2. This equals E raised to the 2k power. So this is E to the 2k equals 2. I'm going to ln both sides. ln E to the 2k equals ln 2. The left-hand side goes pop. And that leaves me with a 2k. The right-hand side just remains ln 2. And so it looks like my k is going to equal ln 2 divided by 2. So that is the growth constant. And we put that in our calculator and round to 4 decimal places. So when I did that, I ended up getting 0.3466. That's the growth constant, and that answers part A. So, gotta get another piece of paper, because part B says find a function which models the wildcat population in terms of t years. So this formula right here, we almost had it when we wrote that down. Now we know what k is. K is 0.3466. So for part B, I'm going to go ahead and write that down. Okay. So for part B, I'm writing the orange formula down. N equals 85 e to the 0.3466 times t. And you can write that as n of t if you want. I'm going to go ahead and box that. That's part B. So a lot of the work for part B was found in part A, finding the growth constant. Let's go ahead and do part C. Part C says, so let me just point out that this thing, if you want to think of this, it is a function, n of t. Part C says, what is the population after 5 years? Round to the nearest wildcat. Yeah, we don't want to start chopping wildcats up. So we're going to go n of 5. And we're going to put that into our calculator. And when I did that and I round it, I ended up getting the population being 481 wildcats. And that's the prediction, okay? So sometimes things change. There could be a big forest fire, or developers come in, and this formula here can change over time. So you don't want to use this formula for like 50 years out, because then it's probably going to be different. But it will model something with an exponential growth or something like that. Okay, so problem D. Did I make it go off beyond? Let's see if I did. Oh, you can barely read it there. There we go. How long until there are 1,000 wildcats round to the nearest year? Okay. So we're still looking at this formula. Part B has the answer to what we're looking, what we'll use. And it says how long, which means T is what we do not know, but they tell us N is 1,000. Okay, so we're going to plug these guys here. Well, actually, we don't have a T. We're going to plug it into that equation and solve for T. And this kind of reminds us of maybe what we were doing with the banking problems. So I have 1,000 equals 85 e to the 0.3466 t. Okay, I'm going to go ahead and I'm going to divide, maybe I'll write it as a fraction, both sides by 85, and oh man, what am I doing here? I end up getting 1,000 over 85, or, so let me write that out. 1,000 over 85 equals this. And I reduced that in my calculator and got 200 over 17 equals e to the 0.3466 t. An exponential equation, I'm going to ln both sides. So ln 200 over 17 equals the ln of e raised to the 0.3466 t. And on the right-hand side, this thing goes pop. And this right here is a decimal point. It just got smeared by the highlighter. And so what I end up having is ln 200 over 17 equals 0.3466 t. I'm going to divide both sides by 0.3466. And I'm going to end up getting something on the, I'm going to get this. So this is what I'm writing on my thing right here. Over 0.3466. So let's do this. ln 200 divided by 17 divided by 0.3466. Now I'm getting t equals 7.11224472, etc. Okay. So they told me in this problem, round to the nearest year. So this is measured in years, so this rounds to 7 years. So 7 years. That's how long it will take with this model for the wildcat population, which is currently 85, to get up to 1,000. And so let's go ahead and do another problem here. Let me show you something first. Now, some of you can skip to the next problem, number 4. When you see number 4 and the type come up, you can do that. But I think I'm going to go ahead and show you something. And this is just optional. I'm going to use purple for optional. When we plugged the K, when we found out what K was, we went like this and we went 85 E, and then we put, 0.3466 times T. I'm actually going to put the ln 2 over 2, and then this is times T. I'm just going to do this. Now, I'm not doing anything wrong, but I'm actually putting the exact value in for K. I'm going to show you what happens. And once again, this is you probably don't want to do this in your homework, but look at this. E, so I have a T over 2, which is in front of that logarithm. And so what happens is I'm going to go ahead and make this T over 2 jump up and be the exponent, because this is the power rule of logs. And then what I'm going to do is I'm going to realize that this thing right here, I think it's property 4 of logarithms, that thing goes pop, and I end up getting 85 times 2 raised to the T over 2 power. So that formula, and compared to this formula here, they're both the same formula. Now this is an approximate formula because we rounded to K. This is an exact formula. So some of you might go, well, this formula is better. Yes and no. In terms of calculations, especially in terms of doing problem D, the formula we have here is better because it has an E, and notice when we ln both sides, that thing goes pop. When you have to do calculations and there's a 2 to something, our calculators just have ln's and logs on it, and even though this formula is a good formula, it's going to be harder to do problems like Part D. So, but this model does have, I mean, we have an E to something, but you can model it precisely with 2 to a power. So this right here is just optional, and I'll include it in the PDFs. But please, for the most of you might want to ignore that. Okay. Problem number 4, our last problem that we're going to do in 6.5, and this will finish chapter 6, is iodine 131. The half-life of the isotope iodine 131 is 8 days. You are given a 5-gram sample. So there is another formula that looks like the Pert formula. The amount, this is called radioactive decay. The amount of a substance equals the initial amount, that's like the principal, E to the rate times T. So that is what we have here, and they give us something called the half-life. This is new, and it says you're given a 5-gram sample. So that is your initial amount. That 5 grams is A naught. You could say that's really the point 0,5. I mean, if you like, because it's the initial amount. I'm just going to go ahead and plug 5 in for A naught. So I only have one other constant that I have to find out what it is, and that's K. So half-life, okay, so what does this mean? The half-life is 8 days, which means this thing is decaying. You have 5 grams, and this is at time 0. The time is measured in days. So what half-life means is this thing's deteriorating, which means after several days you're going to have less than 5 grams. Well, it's just saying for half-life that at 8 days you're going to have half of what you started off with, which would be 2.5 grams. So what you want to do is stick that into this equation to figure out what K is. Now what is that? That's the data point 8, 2.5. Where you have time, amount, input, output. So let's go put that in there. We have 2.5. We're asked to find the constant. This equals 5e raised to the k times 8 power. I'm going to divide both sides by 5. 2.5 over 5 is 1/2. This equals e raised to the 8k power. So e raised to the 8k power equals 1/2. I'm going to ln both sides. On the left-hand side, this thing goes pop, and I'm just left with 8k equals the ln of 1/2. I'm going to go ahead and divide by 8. K equals ln 1/2 divided by 8. So when I do that on my calculator, ln 1/2 divided by 8, I end up getting the rate of -0.08. They tell me to round to 4 decimal places. Let's see, 866, and that is the value of K. Okay, so now because things are decaying, this is called radioactive decay. I'll just put that here, radioactive decay. It means our growth constant is going to be a negative number. Let's go ahead and answer the other questions. So part B says find a function that models the isotope in terms of T days. Now this isotope helps actually detect how well the thyroid is functioning. So, you know, I mean, this is important in the medical world. And so this is what they're asking us to find, but now we know what K is. We just found K. So I'm going to go ahead for this was part A. For part B, I'm writing down that orange equation. A equals 5e to the negative 0.0866 t. So there's the answer, and that A can be written as A of t. Part C says, what is the amount after 10 days, round to 2 decimal places? The amount after 10 days is A of 10. You put 10 in for T, and what I'm getting is 2.10 grams. Okay, so these things are measured in grams, not wildcats, and so this is actually less than half. And we're not so surprised because after 8 days, that was the half-life, it's 2.5, and after 10 days, it's even less. Part D says, how long does it take for 90% of the material to decay, round to 2 decimal places? Okay, so how long for 90% of the material to decay? If you start off with 5, okay, so we're using this formula here. We want 90% of that to decay, so we're only going to be left with 10% of that. 10% of 5 is the amount that we want to see. This is going to equal E to the, so we're writing the formula right here, and so when they say 90% of the material is going to decay, it means 10% is left, and that's what I'm putting in for A. 6t. And so now I'm going to go ahead and solve for T. So this is 0.5 equals 5e to the negative 0.0866 t. Divide both sides by 5. And so this is actually going to do, if you do this in your calculator, or maybe you don't need your calculator to do that, you end up getting 0.1 or 1/10. I ln both sides. And maybe you already know what's going to happen on the right hand side. That thing's going to go pop, and I have ln 0.1 equals negative 0.0866 t. I divide both sides by that negative 0.0866. And I do that in my calculator, and that should give me what T is. And what I ended up getting for T, and I'm supposed to round to 2 decimal places, is, let's see, ln 0.1 divided by negative 0.0866, 26.59 days. And that's how long it takes to get down to, so you only have 10% of this radioactive element. This completes 6.5. We're done with chapter 6. And work on your homework. Stay caught up. I'll see you next time when we get into chapter 7.